Rotational motion is around us in all places. However, conceptually and mathematically, it is more challenging than translational motion. Often the two motions appear together. One of the most useful concepts when the two motions are combined is that of rolling without slipping. As straightforward and familiar this concept might appear, it is the source of a lot of headaches. Resembling the way sophists in ancient Athens were twisting truth to tilt courts to their favor, Aristotle has presented a similar argument to motivate students to think about rolling without slipping and the correct way to apply the mathematical condition. To beginners, Aristotle's argument appears correct, only for them to realize from the conclusion that it cannot be right. Hence, beginners who apply the condition of the rolling without slipping uncritically can become utterly perplexed, and the argument has been named Aristotle's paradox for its paradoxical conclusion. The perceived paradox is easily resolved by understanding and applying correctly the physics behind the mathematics of the rolling without slipping condition. So, what is Aristotle's paradox? Consider a wheel that is rolling without slipping and focus at the contact point A between the wheel and the ground. After one full revolution of the wheel, the contact point is now at the location A'. The length of the segment AA' is equal to the circumference of the wheel, or 2 times pi times r, where r is the radius of the wheel. Then, if O is the center of the wheel, consider the middle point B of the spoke which connects O to A. Obviously, this point has rotated exactly once, if point A has rotated once. However, point B corresponds to a circle of radius r/2. Therefore, as a consequence of the rolling, the length of the segment BB' must be equal to the circumference of this smaller circle, or pi times r. And since the length of the segments AA' and BB' must be equal, we necessarily conclude that 1 is equal to 2. The same argument can be made for any point C on the semi-infinite line that starts at the center O and goes through point A. If point C is at distance lambda times the radius from the center, with lambda any non-negative number, the previous reasoning implies that any lambda is equal to 1. Obviously, this result is nonsensical. Pause the video here to give yourself time to think about the resolution of this paradox. When you are ready, resume play. The source of the paradox lies on the misunderstanding what rolling without slipping implies. The mathematical condition which quantifies this smooth rolling has been applied incorrectly. The wheel performs 2 motions, one translational and one rotational motion. The translational motion translates the wheel parallel to itself. All points of the wheel in this motion have the exact same velocity, indicated by capital V. The rotational motion happens about an axis that passes through the center of the wheel O. All points of the wheel rotate with the same angular velocity. However, each point has a different rotational velocity. Given the angular velocity omega of the wheel, the magnitude of a point's rotational velocity is omega times little r, where little r is the distance of the point from the center O. Each point of the wheel has a total velocity, which is the sum of the translational and rotational velocities. The result is a complicated pattern of velocities for the points of the wheel. Looking at the point A, we see that the two velocities are opposite. In general, the sum does not have to vanish. If the sum is non-zero, then point A has a total velocity and slides on the ground. The condition rolling without slipping requires that such slipping does not happen. In other words, the total velocity of the point A must vanish. Hence, the rolling without slipping condition is a condition for the point A and only point A. This condition establishes a relation between the translational motion and the rotational motion, which would otherwise be unrelated. More precisely, it states that the translational speed equals the angular speed times the radius of the wheel. Therefore, for the contact point A, the length of the path AA' does not include any amount from slipping. However, this is not the case for other points on the line that joins the center with the contact point, simply because the rolling with slipping condition does not apply. Point O, for example, does not participate in a rotational motion. Its path, OO prime, is solely due to sliding by speed capital V. Hence, the length of OO prime is equal to capital V times the period of the rotations. At the same time, using the rotational speed of point A, we can express the length of AA prime as this rotational speed times the period. Then, the rolling without slipping condition guarantees that the two lengths are equal as required from geometry for the sides of the rectangle O, A, O prime, A prime. Let's look at point B now. Adding its rotational and translational velocities results to a total forward velocity with magnitude capital V over 2. This is half the velocity of point O. As a result, point B slips by an amount which is half the length of OO prime. The rotation of B about the center contributes the other half, the amount used in the statement of the paradox. Hence, the length of the segment BB prime is equal to the length of the segment AA prime, and no paradox emerges. In general, given a random point C at distance lambda times r from the center, the point has rotational velocity lambda times capital V. Adding to this the translational velocity, we find a total velocity equal to 1 minus lambda times capital V. That is, the point C either slips forward if lambda is less than 1 or slips backwards if lambda is greater than 1. The amount of slipping is given by its total velocity times the period, and it is equal to 1 minus lambda times the length of segment A prime. The total distance covered by C in one period is the sum of the slipping distance and the distance traveled by C due to the rotation. The latter is equal to the circumference of the circle of radius lambda times r. Equivalently, is lambda times the circumference of a wheel. Adding the two distances, we conclude that the length of segment CC prime is equal to the length of the segment A prime. We have thus resolved Aristotle's paradox. The key observation is that only the contact point has vanishing total velocity. Any other point on the same spoke has a non-vanishing velocity, which adds a slipping length to the rotational length. Aristotle just ignored the slipping length, and this created the paradox. For the resolution of Aristotle's paradox, many people often state that different points on the same spoke of the wheel move on distinct trajectories. The contact point moves on a cycloid curve, while points B and C move on curves which are different from a cycloid one. More precisely, point B traces a curtate trochoid, and point C, with a distance from the center greater than the radius, traces a prolate trochoid. However, these paths are irrelevant for the resolution of the paradox, and they're introduced due to a misunderstanding of the actual problem. For example, the length of the cycloid curve for one period is 8 times the radius of the wheel, which has nothing to do with the circumference of the wheel, which is 2 times pi times r. The misunderstanding comes from the incorrect interpretation of what the point A in Aristotle's paradox represents. The people who suggest to look at the trochoid paths treat the points A, B, and C as marked points on the wheel. Hence, they paint a point A on the rim of the wheel, and they follow this painted point. In this case, indeed, the sequence of positions of the marked point traces a cycloid curve which starts at A and ends at A prime. The painted point is a real particle, and the cycloid is the path performed by this real particle. In the video on screen, the reflector on the front wheel marks a real point B. Hence, the reflector moves on a curtate trochoid. It is evident that given two distinct points, say at distances less than the radius of the wheel, although they are both trace curtate trochoids, the curves have different sizes and hence different lengths. Therefore, there is no way that the resolution of the paradox be given using these paths. The point entering the discussion of Aristotle's paradox is an imaginary point, not a real particle. The paradox uses the instantaneous center of rotation, the point where the total instantaneous velocity vanishes. This is not a particular point of the wheel. The sequence of positions of the instantaneous center of rotation used in the rolling without slipping motion of the wheel forms the straight segment, A prime, on the floor. If we had painted the points of the rim with different colors, then we would see that, at each instant of time, The instantaneous center of rotation corresponds to a different wheel point, that point of the wheel which finds itself in contact with the ground. Notice now that point A, the instantaneous center of rotation, does not move on a circle. It just happens that the circle of radius covers the interval, A prime. This covering, in physics, is equivalent to saying that the wheel rotates purely about the instantaneous center of rotation and, hence, its name. Aristotle pretended that this fact is true for other points of the wheel, but it is not. So, to conclude, Aristotle's paradox is completely a physics paradox. It is created by the combination of translational and rotational motion and cannot be resolved by purely mathematical concepts that do not contain any physics. And with this comment, we have concluded today's presentation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more lectures. Thanks a lot for your support.